Welcome back to the module Waves. In this unit we'll be discussing standing waves. Now, you have seen oscillations in time, oscillations in space, and even oscillations in space-time. These were the traveling waves. Now, in this case we will be dealing with standing waves. In the standing wave we have oscillations in time and oscillations in space, but the oscillation in space is in this case fixed. So how do we make standing waves? Now consider I have a rope that I fix between 2 points, for example to the wall. Now, if I start oscillating this rope, for example at the center, with an harmonic oscillation at frequency omega, what happens? Now, from the previous unit you know that we will get 2 traveling waves that move to the left and to the right. These of course are the solutions that we have discussed before. Of course, when these traveling waves reflect to this fixed point, to the wall, they will be reflected back and traveling the other side. Again, both for the left and the right hand side. So the end result is that we get interference. And you see a picture of that right here. Now note that when these 2 waves move in opposite directions and they interfere, the result is a wave pattern that is fixed. So the spatial pattern is fixed, but every point oscillates at frequency omega. In mathematical terms, we can calculate the total amplitude, U total, being the sum of a wave that propagates to the left and a wave that propagates to the right. And if you do the trigonometry right, you see that the total amplitude is equal to 2 times A times sine kx cosine omega t. So the wave is a spatial wave, sine kx, times a temporal wave, cosine omega t. Now, there's only one catch. In this case, we cannot choose an arbitrary k for this spatial part, because we have to fulfill the boundary conditions. At the boundaries of this wave, their amplitudes needs to be 0, because these points are fixed. So what waves can we choose? Now, then we have to look at this sine kx part. So the simple solution is for the solution where sine kx equals to 0 at 0 and at the other side of the rope. In this case, we can obtain that by choosing a wavelength that is equal to 2 times the length of the rope, 2L. You can see here that both at the left hand side and at the right hand side the amplitude is 0 and there's an oscillating pattern in between. This is what we call the first harmonic, and the frequency of the first harmonic is V divided by the wavelength, is V divided by 2L. We can have other solutions as well. So for example, looking at the second harmonic. In this case, the wavelength is equal to the length L, and we get a frequency V divided by lambda is V divided by L. This is what is called the second harmonic. Also, we can have a third harmonic and a fourth and a fifth harmonic. In the third harmonic, the wavelength is equal to 2/3 of L, and the frequency is F is 3 times the velocity divided by 2 times the length. Now, as you have seen from these animations, there are certain points that oscillate with a large amplitude and some points that don't oscillate at all, that have amplitude 0. These are called nodes and antinodes. Now, the nodes are the points with 0 amplitude. This is the case when sine kx equals to 0. Now, you know that this is the case when kx is equal to 0, 2 pi, to 2 pi and 3 pi. This occurs then at locations of x equal to 0, lambda over 2, lambda, 3 lambda over 2, etc. For every wavelength that is a solution to these boundary conditions. Now, you can also have antinodes. These are the points with maximum amplitude, and they occur where sine kx equal to 1. In this case, this occurs at kx equal to pi over 2, 3 pi over 2, 5 pi over 2, etc., etc. Now, the locations of these oscillations, these antinodes, are at x equal to lambda over 4, 3 lambda over 4, 5 lambda over 4, etc. So let's introduce these nodes and antinodes now, for example, and look at them in the second harmonic. So in the second harmonic, the wavelength is equal to the length L, and the frequency is equal to V over L. Now, the nodes, these are the points in red, where the amplitude is 0. They occur at x equal to 0, lambda over 2, lambda, 3 lambda over 2, etc. And indeed, if we now fill in this lambda equals to L, we find that x equal to 0, L over 2 and L are the nodes of this second harmonic oscillation. Now the antinodes, these are the points with maximum amplitude. They occur when x equal to lambda over 4, 3 lambda over 4, 5 lambda over 4, etc. And these are the points then with x equals L divided by 4 and 3L divided by 4, the points where the amplitude of the standing wave is at its maximum. Now, an important application of standing waves are in music instruments. But let's first consider music instruments with strings, for example the violin or the guitar. In these instruments there's a wave that propagates through the string and the string oscillates in a perpendicular direction with respect to this wave propagation. So that means there are transverse waves in these strings. Now, the temporal frequencies of these string oscillations are given by omega is k times v, where v is the propagation speed of the wave inside the string. This propagation speed v is equal to square root of the force divided by the mass per unit length. So this gives the propagation speed of the wave in the string. That means that larger masses lead to a lower speed and larger forces lead to a higher speed. Again, the frequency of oscillation is equal to 1 divided by lambda times square root of fs divided by mu, where of course lambda can be the solutions for the standing wave, the different harmonics. So let's consider now the violin. In the violin, the strings are connected at 2 fixed points, so they are both closed. Now when you strike the violin, you get sound from all the harmonics. They all contribute to the sound of the violin. This is called the timbre, and this gives this warm sound. In contrast, when you pluck a guitar, you only get the first harmonic, or the first and the second harmonic. So this gives a totally different sound. Let me demonstrate these concepts to you with a guitar. So here is the guitar, and on the bottom you have the high E note, and here at the top you have the low E note. Now, the high E note is much lighter. That means its mass per unit length, mu, is much smaller. Therefore, it gives a higher pitch. Instead, the low E note is much heavier. So mu is bigger, and therefore the pitch is much lower. And secondly, I can also tune the guitar. I can do that in 2 different ways. First of all, I can change the length. So, for example, in this case, with the high E, the length is the total length from top to bottom. But for example, if I halve this and I put my finger here, then the length is only half the total length. That means that the pitch is twice as large. Now finally, I can also tune the guitar by changing the force that I apply on the string. So for example, the high E string, I can detune it by applying more force, and therefore the pitch of the guitar goes up. Another type of instruments that have standing waves are instruments with pipes. In this case, the pipe is filled with gas where the wave propagates, and the oscillations take place in the direction of propagation, where the oscillations are densifications of the gas. The temporal frequencies again are given by omega is equal to k times v, but in this case v is given by the square root of gamma kBt divided by m, where capital T is the temperature, m is the mass of the molecules in the gas, gamma is the heat capacity ratio, and kb is Boltzmann's constant. So again, here we can calculate the frequency of oscillation as equal to 1 over lambda times square root gamma kBt divided by m. But again, here the wavelengths that are supported by this pipe are given by the boundary conditions of the pipe. And they can be in this case, be open and closed. So for example, if we look at the trombone, we blow the trombone at the entrance with our mouth. So there we have a closed point. But of course at the exit we have an open trombone, and there the gas is freely to oscillate. So in this case we have a displacement note at the entrance and a displacement antinote at the exit. This gives us a fundamental harmonic that has a wavelength that is equal to 4 times the length. In contrast, if we look at the recorder, we blow the recorder as an open entrance, and also of course at the other side the recorder is open. So in this case we have 2 open boundary conditions for the oscillation to occur in the pipe. We have a displacement antinote at both the entrance and a displacement antinote at the exit. This gives us a fundamental frequency lambda equal to 2 times L. So let me demonstrate these concepts to you with the recorder. So essentially the recorder is just an open pipe. It's open at the entrance and open at the exit. And I can change the pitch in 2 different ways. First of all, I can change the velocity with which traveling waves run through the pipe by blowing harder or slower. Let me show it to you. So I blow harder, therefore the velocity goes up, and therefore the pitch goes up. I can of course also change the length of the pipe. So when I change the length of the pipe, for example by closing holes, the pipe becomes effectively longer, and therefore the pitch goes down. Let me show it to you. So you've seen that the pipe becomes essentially longer and the pitch goes down. So in summary, I've shown you that standing waves occur as a result of the interference between traveling waves, that the boundary conditions determine the wavelength and the locations of the note and the antinodes, and that the pitch is determined by the mode wave velocity and the wavelength that is supported by either the string or the pipe.